So the quantum mechanical model explains a lot of stuff, and that's why we torture you with it, right? So the chemical properties of elements are periodic because the number of valence electrons is periodic. So we see that elements in the same column have similar properties. They repeat that pattern because the number of valence electrons repeats in the same pattern. If we look at the noble gases, group 8A, they all have 8 valence electrons except for helium. They are especially non-reactive. Helium and neon are practically inert. They just don't react with anything. And the others react with very, very few things. So why is this? Well, atoms that have 8 valence electrons are unusually stable. The overall energy of the electrons is lower when that quantum level is full. And so these guys are very stable because they're at a low energy.
Is that because it has shielding and everything?
Well, it has to do with the full valence shell. So you've got the s orbital and the p orbitals are all full. And so we see that what's changing here, other than helium, is you've got S2 and P6, and all that's changing is the level, 2, 3, 4, 5, 6. They're all the S2, P6. When you've got the S2 and the P6 sublevels full, that's a lower energy state. These guys don't react much because if they react, they often go up in energy, and why would they want to do that? They are just full of themselves. They're just cool all by themselves. So I think of these as the kids in high school that had it all together. I was not one of those kids. But the kids that everybody else wants to be like, right? These are the guys that have arrived. That's why they're so non-reactive. If we look at elements that are close to the noble gases on the periodic table, we see that they're very reactive. So if we go one column past, and really the periodic table should be more like a spiral, right? Because why is there a break between neon and sodium? It's like a flat map of the globe, right? The Earth is round, but it's inconvenient, so we cut it somewhere and make it flat. Periodic table, same thing. So group 1A, these elements all have 1 valence electron. They are 1 electron past a noble gas. The noble gas is especially low energy and stable. So if these guys were to lose that 1 extra electron they have, then they're going to have the same electron configuration as a noble gas. They do not become the noble gas because the number of protons doesn't change. So I think of the electrons on the atom as being like your clothing, right? So the clothing is on the outside. Who you are is deep, deep on the inside, right? That's your personality, your soul. You can change what you look like. You can color your hair. You can cut your hair. You can wear different clothes. You can do all kinds of things to yourself, but it doesn't change who you are. So these elements are not very stable because they're higher in energy, and they can very easily become lower in energy by losing 1 electron. That's why they react very readily to form +1 ions, because by losing 1 electron to form a +1 ion, they now have the same electron configuration as a noble gas. The halogens are just on the other side of the noble gases, and they are also quite reactive. These guys are 1 electron short of a noble gas configuration, right? They all have 7 valence electrons. The noble gases have 6. 8 is like, the noble gases have 8. 8 is like a magic number. It's like what everybody wants. You want to have 8 electrons, and we'll see that over and over again. There's even a rule called the octet rule. So they want 8 valence electrons. So these are very motivated to gain 1 electron, and then they have the noble gas electron configuration. They do not become a noble gas, but they have the same electron arrangement. Okay? So these form anions with a 1- charge. We learned that sort of not empirically, just I don't know what the word is, without understanding why, when we learned about nomenclature and ions and things, right? Well, group 7A, they form -1 ions. The quantum mechanical model explains why they do that. So there's definitely patterns in electron configuration and ion charges. So we can predict the charge of ions based on position in the periodic table for many elements. So group 1A elements form +1 ions. Group 2A elements form +2 ions. Because if they lose 2 electrons, then they're like a noble gas. The group 7A form 1- because they need to gain an electron. Group 6A has a 2- charge because they need to gain 2 electrons. You go over to group 5A, they need to gain 3 electrons, and so they have a 3- charge. So they make ions that result in an electron configuration that's the same as the nearest noble gas. Does that make sense? They're trying to be like the cool kids in high school. I remember when my oldest son was in high school, the cool thing was Hollister hoodies, right? And you go to school and everybody's wearing Hollister hoodies, and he just had to have a Hollister hoodie, right? Because we need to express our independence and look alike. Yeah. We all did it. I did it too. But you want to dress like the cool kids because then you think maybe some of their coolness will rub off on you. I don't know. So here's a chart showing elements that form ions with predictable charges. And I crossed these out because in the textbook it's numbered wrong. And I see why they did it, but it's still wrong. They're not showing the first period. And so they left that off and they just numbered 1, 2, 3, 4, 5. But that's wrong. So, but these guys form +1, +2 over here, -1, -2, -3. I don't know why they always leave phosphorus out, because phosphorus does form a -3 ion. So I'll put them in there. P3-. Here's aluminum.
What is it supposed to be showing?
This is showing the elements that form ions with predictable charges. Yeah. There are a couple others. We learned that zinc and silver have predictable charges, but it's not predictable because of looking at these electron configurations.
What about barium?
Barium is predictable.
Or not barium, BE, what's BE?
Beryllium.
Beryllium.
Yeah, beryllium's weird. So if you needed to make an ion with beryllium, I would expect you to make a 2+ ion. So we just kind of, some of them are a little weird. Okay, so this is really what we learned earlier in nomenclature, but now, hopefully, it makes a little more sense why it's like that. Okay, so we wrote electron configurations for atoms. We can write electron configurations for ions as well. So an anion forms when a nonmetal gains an electron, or more than one electron. They will gain electrons to fill up their valence shell so that their electron configuration is the same as a noble gas. So let's look at sulfur. So here's sulfur atom. Here's 1s2, 2s2, 2p6, 3s2, 3p4, sorry. So it's got 6 valence electrons. That's the atom. The ion, the S2- ion, 2- means we added 2 electrons. So then we add 2 electrons to the electron configuration. Now we have 3p6 instead of 3p4. This is the same electron configuration as argon. And that is why sulfur does that, because that's lower in energy. Any questions? When you write the electron configuration for an anion, you're going to add a number of electrons equal to the charge on the ion. Cations form when you lose electrons. Metals generally lose all their valence electrons. For the main group elements, they always do this. And so what happens is they're losing their valence electrons, and then what's underneath? Another level, right? So let's think about the onion, right? So you take off the partial skin on the outside, and you take all of that off. What's underneath? A nice full layer of onion, okay? So if we look at magnesium, magnesium's electron configuration, it's got these 2 valence electrons. So if we get rid of those, we get a 2+ ion, and now 1s2, 2s2, 2p6. Now the second level is the valence shell, because we lost all of the 3-level electrons. So now it's got 8 valence electrons. It's got the same configuration as neon. It isn't neon because it has a charge that has a different number of protons, but the electrons are the same. It's dressed the same.
So instead of writing the whole configuration like that, could we just put brackets and then NE next to it?
That's a good question. So for the magnesium ion, could you just say, well, this is Ne? It depends on how the question's worded. We need to understand what's going on. And understanding what's happening with these electron configurations is actually more important than being able to write them out. That certainly is true, that it's this. Whether the question is wanting you to show that or not, or show this, it kind of depends. Any other questions?